I'm going to show you how an equilibrium works with this handy model. Let's say that everything in this beaker is our reactant and everything in this beaker is our product. And we can see through this demo how at equilibrium the same amount of product and reactant are being made, even though it may not appear that way, even though there may be more reactant and less product, or more product and less reactant. As we know with weak acids, very little product is made, and that's what makes it a weak acid. We don't have a lot of H pluses in solution, and the H plus would be our product. I'm going to represent the creation of product and reactant with my two different size beakers. Since we know that not a lot of product is made, we'll be using a 10 milliliter beaker to represent making product. And I'll be using a 150 milliliter beaker to show product being made back into reactants, because this is a reversible reaction because it's at equilibrium. Currently, we're at the start of a reaction. We have all reactants and no product. We are not at equilibrium because we haven't made any product, nothing's happened. So we'll start with the first one. For the first one, I'm going to dip into both. We see that I'm not getting any product because there's none, but I'm making some product with reactant, and I'll just keep going. And you can see that currently right now, before I reach equilibrium, I'm mostly making product. Maybe a tiny bit of reactant, but I'm really only making product. This is a one-way reaction for now. Let's stop for a moment and fill in our sheet. At the start of a reaction, we have 100% reactants. So let's first label. We'll put our reactants on the left side and our products on the right. And I'll color in. So we have 100% reactants. So I'm gonna draw this red as we saw in the demo. And there's nothing in the product side. And that means that this reaction is a single direction reaction. Only goes in the forward direction. I'll call products to reactants forward, and products back to reactants, that is the reverse reaction. So in the beginning, a reaction is one direction. Because it only makes products. And this is because there are no products to go in the reverse direction. So there's no products for the reverse reaction. And that makes it a one-direction reaction. As soon as there is product to be made back into reactant, the backwards reaction will happen. However, it will happen at a much slower rate due to it not being at equilibrium yet. As of right now, we can see that I'm scooping very different amounts. After the reaction has proceeded for some time, we get to this middle of the reaction, where we have about 95% reactants and about 5% products. So again, I'll label reactants, products, and I'll draw some of my reactants in. And now we have some product. Not very much, but we have some. And this reaction is reversible now. However, the rates are still different. As the reaction proceeds, the forward rate of reaction is faster than the reverse rate for this middle of the reaction part. So the forward rate of reaction is still faster than reverse rate. This causes an increased production of product overall. So at this point, we still have more product being made than reactants are being made. So the forward rate is still greater than the reverse rate as we're moving towards equilibrium. And I can keep going. And at some point we'll get to where I'm transferring the same amount back and forth, even though there's more reactant than there is product. We might be at that point. If we read the front of our beakers, you'll see that they don't change after a while. You can see here that the amount of volume in our product side is remaining constant at 150 milliliters, while on our other side, our volume is staying constant at 900 milliliters. So we're seeing that even though I'm transferring the product and reactant, the amount is staying the same, and therefore we can conclude that the amount I'm transferring is also staying the same. Even though I'm making product and reactant, and even though they look like they're different amounts, they're actually the same. Because there's only so much product that I can grab with this large beaker. And I could keep doing this forever. And the amount of reactant and product will never change, because now I'm at equilibrium. Every time I'm transferring the same amount. And that's what it means to be at equilibrium. Equilibrium does not mean that you have the same amount of reactants and products. It just means that you're creating the same amount of products and reactants. When we reach equilibrium, in my reaction, just for this demo, we have about 86% reactants and about 14% products. And I just got those numbers by looking at how many milliliters I had. I had about 900 milliliters in my reactant vessel and about 150 milliliters in my product vessel. And at this point, when our reaction reaches equilibrium, as you can see in the demo, I'm transferring the same amount. So my rate of reaction is the same in the forward direction and in the backwards direction. So I'm going to show that by drawing my arrows the same size. These arrows show rates. So when I draw them at the same size, that shows that the rate is the same. So when the reaction reaches equilibrium, the rate forward and back are the same. So I'll say the forward rate and reverse rate are the same. That means there's an equal amount of product and reactant being made. Equal amount of product and reactant being made. This means that the amount of reactant and the amount of product, this should be a P product, are being held constant. So this is holding amounts constant. Meaning, no matter what I have, I'm always going to have 900 milliliters and 150 milliliters until I shift something in the equilibrium. But as of right now, at equilibrium, the rate forward, the rate backwards are the same. So I'm always going to have 900 and I'm always going to have 150. And that's what is at equilibrium. So our rate is now the same. And that's equilibrium.